So that's what we got last time, which is basically the tangential component of electric field is continuous at the boundary. We showed that, and also we showed the tangential component of magnetic field is continuous at the boundary, right? And we derived the law of reflection and Snell's law using the boundary condition. Now let's use the boundary condition to the electric field and the magnetic field for two types of polarization. So we have E perpendicular. We touched a little bit on this one last time, E perpendicular and E parallel. So the plane of polarization, we have two planes here. One is plane of polarization, which is the plane formed by this magnetic field, electric field, the plane formed by this incident light or this k vector, this kr vector and kt vector. So we have incident part, incident light, reflected light and transmitted light, and also we have normal. So those things form a plane. So we have this plane. So this plane is called plane of incidence. Okay. And we also have a plane that defines the boundary. So this plane, which is also the surface of the boundary, that's the boundary plane. Now when we talk about this E perpendicular and E parallel, so what that is this E perpendicular is the electric field that is perpendicular to this plane of incidence, okay, and this E parallel is the electric field or the component of the electric field that is parallel to this plane of incidence. Yeah. So for example, in this particular example, this electric field is coming out of the screen, right? Here dot means it's coming out of the screen. That means it is perpendicular to this plane of incidence. So here we are talking about E perpendicular. Okay. In the next part, we'll also talk about E parallel, but for this discussion, let's talk about E perpendicular. So for E perpendicular component, so our first boundary condition is tangential component of electric field is continuous. That means the electric field on this medium and the electric field on that medium is continuous. So that means the total electric field above the boundary is equal to the total electric field below the boundary, which is what we have here. So this is again EOI and EOR are perpendicular component, which is the tangential component. Okay. So if you think about this electric field, it is parallel to this plane, right? This boundary. It is perpendicular to the plane of incidence, means it is parallel to this plane. Does that make sense? This is, it's pointing in, but it is perpendicular, it is parallel to this plane, this surface, right? And our boundary condition is basically the tangential component of the electric field is continuous, right? Ti plus tangential component. Let's just say these are the tangential components. Now the magnetic field, the tangential component of the magnetic field is also continuous, but the magnetic field here we have it is oblique, okay. It is not entirely along this plane. So in order to get the tangential component of the magnetic field, we need to resolve it, right? So we have this component of this magnetic field and this component. Okay, let me use a different color. So we have this component and this component. So our boundary condition needs this component. Let's see, this component, right? Does that make sense? This is the component that is parallel to this plane, because we need the component that is parallel to this plane, not the perpendicular component, not this one. That's the boundary condition, if you remember our boundary condition here. So this is the tangential component. We are talking about the component that is parallel to this boundary, okay, parallel to this plane, I should say. So that means we need this one, and this one is BOI. So you can show that this angle and this angle would be equal. If this is theta I, this would be also theta I. So this would be BI cosine theta I, and it's pointing to the left, so you will have minus sign. Okay, so that's the tangential component of the magnetic field that is pointing to the left, and this is the tangential component of this one, this magnetic field. So this magnetic field also has this component and this component, and we are interested in this one for the boundary condition, and this is BOR. If this is theta R or theta I, this will also be theta I. We can show that. Okay, that's something you can do. So this would be BOR cosine theta I, and it is positive because it's pointing to the x-axis, positive x-axis or positive side. So this plus that is the total amplitude of the magnetic field above this boundary, which would be equal to the total magnetic field below the boundary because of the continuity condition. So that means the tangential component of that would be that. Okay. So we have two equations, this one and this one. Now we want to write both in same variable. So we want to write this B in terms of E, and we have this relationship between B and E. If you remember from our previous chapter, we derived the relationship between B and V, right? B and E. So B is E over V, and V, from the definition of refractive index, N is C over V. So we can write V is C over N. So we write V is C over N. That means B would be equal to N over C times E. So now we substitute this B in this equation. Okay, so for all these B's, use this equation and turn that in terms of E. So you substitute B in this equation and write in terms of E, and you get this equation. Okay, so in the left side we will have N, but the N would be for the air, okay, or N would be for the incident medium. So N would be common, and EOI minus EOR. Okay, actually this term would be on the, this would be positive and this would be negative. Okay, we have negative here, that's positive, but we have negative here. If I multiply both sides by negative sign, then I will have let's erase that. So I will have positive here and negative here. Does that make sense? Yeah, I'm just multiplying both sides by negative sign, and then you get rid of negative here, that becomes negative, that becomes positive. Okay. So, and then now we want to basically the purpose here is to get the ratio of the magnitude of EOR over EOI. Okay, we want to get this ratio. This is the amplitude of reflected part of the electric field. This is the amplitude of the electric field that is incident. We want to get that, and we also want to get the electric field that is transmitted over the electric field that is incident. Okay, we want to get these two ratios. These are the ratios of the magnitude of electric field of the reflected part and the incident part, transmitted part and incident part. Okay. So, for that what we need to do is we need to solve these two equations. Okay. We have this equation and this equation. So, we want to solve those two equations. So, to get the ratio, let us divide both sides of this first equation by EOI. Okay, so, divide this by EOI, 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 and I get this one. So, this is basically dividing this first equation by EOI, I get that. Likewise, if I divide this one, the one in this green box, by EOI, I get this equation. Okay, just divide by EOI, 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 and then just rearrange the terms. Okay, so the terms without anything, without the ratio, you put that on the right side, this on the right side, and the terms with this this ratio on the left side. Now, we have these two equations in terms of the variables that we wanted. So, we want this one and we want this one. Okay, these are the ones that we want to get, right. So, we want to get this one, we want to get that. So, we have two unknowns and we have two equations. So, we need to solve those two equations. So, how do we solve those two equations? Yeah, so you eliminate one of the variables, right. So, you can eliminate, let us say you want to eliminate EOT, EOI, or let us eliminate this one. So, to eliminate this one, what you need to do? Yeah, there are different ways to solve this, right. So, one way is, let us see. So, we have these two equations and I want to eliminate this one. That means, let us divide both sides by this term Ni cosine theta I, here also Ni cosine theta I, here also Ni cosine theta I. So, when you do that, you get rid of that and you also get rid of that, and then you add the terms, okay, for the two equations. So, we already got rid of that. So, that means this one and this one will cancel, right. So, what is left here on the left side? So, we have NT Ni cosine theta t over cosine theta I, and then here on the top we have, let's see, So, this is for the bottom one, and for the top one we have just 1, right? And I'm taking this EOT EOI out of the parenthesis. Is that right? This thing is from the second term, this one, and this one is now outside the parenthesis. And on the top here we have the same thing here, so we take it out, right? We got that. Does that make sense? And what else we have? We already canceled this one and that one. Now we have this 1 on the right, and then we have this term. This is also 1, right? Plus 1. Is that right? Okay. So then we can simplify this. So nt cosine theta t plus ni cosine theta I over ni cosine theta I. So EOT over EOI is equal to 2, right? Now what should I do to get this, because this is what I want to get? Yeah, just take this thing to the right, right? So if I do that, I get 2 ni cosine theta I and t cosine theta t plus ni cosine theta I. So that's the ratio of the amplitude of transmitted electric field and incident electric field. Okay, so this thing is called transmission amplitude coefficient. So that tells you how much amplitude is transmitted with respect to the incident electric field. In the same way, what else we want to find? Yes, we also want to find this one. So EOR, EOI, and you do the same thing, exactly same thing, just do that algebra. Okay, so when you do that, you get, oops, you get this expression. Okay, so this is the amplitude reflection coefficient. We got amplitude transmission coefficient, we got this one, and in the same way you can also get that. Now why I have perpendicular here, perpendicular, perpendicular? Yes, so basically this is the plane of incidence, and we are dealing with the electric field that is perpendicular to that. So we are dealing with the perpendicular electric field. Now we can do the same thing for parallel electric field, or electric field that is parallel to this plane of incidence. Okay, so let's see that also. Before that, we can look at this problem question. So we want to find R perpendicular and T perpendicular for normal incidence for air and glass interface. So we have this interface. This one is air. Air is 1 refractive index, and glass is 1.5, and light hits normally on that interface. So we want to find R perpendicular and R parallel. Sorry, not R parallel, R T perpendicular.
So when it says normal incidence, we're talking like straight down 90 degrees?
Yes.
Okay.
Not 90, but 0 degrees. we always measure the angle with respect to the normal. Okay, so this would be pretty straightforward, right? So you just use this formula. So you plug cosine angle is 0 degrees, here 0 degrees, here also 0 degrees, 0 degrees, and then our Ni incident is in air, so that's 1. This is 1.5. This is 1. That's 1.5. So what you get? So you get 1 minus 1.5 over 1 plus 1.5. So that's negative 0.5 over 2.5. So that will give you some value negative. And the negative means the phase changes when the light is reflected. Okay, it is 180 degrees out of phase. So what that means is so the electric field will be inverted by 180 degrees.
So it'll be going into the page now?
Yes. Okay. Now let's look at the parallel case. So here is the parallel case. We have this plane of incidence. So this is the plane of incidence. Okay. Again, we have two planes here. Don't be confused with the two planes. We have plane of incidence and we have the plane of the boundary. So this is the plane of the boundary. And this electric field is parallel to this plane of incidence. See, this is parallel to the plane of incidence, right? So this electric field is parallel to the plane of incidence. This electric field is parallel to the plane of incidence. So we are talking about E parallel. Okay. So now let's use the boundary condition. The boundary condition is the tangential component of electric field is continuous. Tangential component means the component that is parallel to the plane or the boundary. So that means our electric field is not parallel to the boundary, right?
Yeah, no, so our magnetic field is completely.
Yeah, the magnetic field is parallel, but electric field is not. So we have two components of electric field. So let's resolve our electric field into two components. We have this component and we have this component. So which one would be parallel to this boundary? This one, right? So this component. So you can show that this angle and this angle would be equal with some geometry. So this would be theta I. So then this would be EOI cosine theta I. Okay. Same thing we can do here. So this component and this component. So this is the tangential component. So this is EOR cosine theta I. This is theta I, and that would be theta I. And we can do the same thing here. So we have this component and this component. So this component would be, this is theta t. So this would be theta t. So this would be EOT cosine theta t. Okay. So the sum of these two electric fields, which are above the boundary, would be equal to that. Okay. So that's what we have here. And they are all positive because they are all pointing to the right. And we have, like you said before, so magnetic field is all tangential, so we don't need to worry about their components. So BOI, BOR is equal to BOT. Now here BOR is negative because it's pointing into the screen. Here it's out of the screen, so it's positive, but into the screen is negative, and down here it's also out of the screen, so it's positive. Now just like before, write just in terms of electric field. So let's write this magnetic field in terms of electric field. So substitute that here, here, and here, we get this equation. Okay, so we are just substituting this equation in this one. We have this refractive index times electric field. C will cancel because C is common, right, because it's speed of light. So we'll have electric field times refractive index, which is what we have here, and the refractive index in the left side would be refractive index in the incident medium, and on the right side would be for the transmitted medium. Now again, the purpose here is to get the ratio EO R over EOI, and we want to get also EOT over EOI. This is what we want to get. So for that, let's do the same thing as before. So divide both sides by EOI, okay, on this one as well as on this one. Divide both sides by EOI, so we get this from the top equation, and do the same thing for the bottom one. We get that. Okay, and then just like before, we want to solve for whatever we are looking for. So when you solve that, so let me show you one. Let's see if I can use color pen here. So let's say we want to get rid of this one and this one in this equation. So to get rid of that, let's divide this by cosine theta I, cosine theta I, cosine theta I, and then let's divide this by ni, ni, ni. So cancel that and that, cancel that and that, and then you add term by term. So this one will cancel that. Now here we have cosine theta t over cosine theta I, and then plus nt over ni, and then you can pull the common terms out. So EOT over EOI, that out, and then on the right we have this one is 1, that's 1, so that's 2. So simplify that, we'll have ni cosine theta I, so that's ni cosine theta t plus nt cosine theta I, that is equal to 2. And okay, so we also have this EOT over EOI. Oops, come on, I cannot write there. EOI. So I want to get EOT over EOI. So that would be equal to 2 times ni cosine theta I over ni cosine theta t plus nt cosine theta I. Okay, so that's what we have. So so that's what we got. This one is we got by solving the equations. Now you can do the same thing for R, this one also, R also, and I'm using here parallel because now again we are dealing with the parallel component. Okay, so we got the reflection amplitude coefficient for parallel component and transmission amplitude coefficient. And these four equations are what we call Fresnel's equation. Okay, so they are, we got four equations for R perpendicular, T perpendicular, R parallel, and T parallel. So these expressions are called Fresnel, but it's pronounced Fresnel equations. We can do the same kind of problem like we did before. It's pretty straightforward, right? You just substitute the values here. So this is also for the normal incidence. So for the normal incidence, you can substitute cosine 0 here, cosine 0 here, cosine 0 here, cosine 0 here, and then I would be 1 and T would be 1.5. Do the exactly same thing. And you will get exactly same number here. And I will show you the graph that whenever we deal with the theta equal to 0 degrees, we get R parallel equal to R perpendicular. I will show you the graph later. Okay, so you can do that. This is pretty straightforward, right? I don't need to do that. Okay, so let's look at the now. Let's now write the equation. Just what we did in the problem. So for normal incidence, when theta is 0, we get these expressions, right? The cosines would be 1, and our equation would simplify to these equations. So that's that. And parallel and perpendicular would be equal for both reflection and transmission. Now let's look at this equation. This is the equation we got for the parallel component. Now there is a condition at which this R parallel would be 0. So what would that condition be? Just by looking at that equation, when would R parallel be 0? No, not ratio. When these two things are equal, they will cancel, right? And then you get this to be 0. So that means if you have this equal to that, then our parallel would be 0. Okay, and then we can use Snell's law in this equation. Okay, so we have this Snell's law. Snell's law is Ni sine theta I is equal to Nt sine theta t. Okay, so that's Snell's law. Now if I use this in this equation, I get this equation. Okay, so I'm substituting this and this expression. So let's see, Ni cosine theta t, Nt cosine theta I. Okay, let me do that. So we have Ni cosine theta t equal to Nt cosine theta I. So if I plug this in here, so I get Nt sine theta t sine theta I cosine theta t is equal to nt cosine theta I. Cancel that, and then move this to the right side. I get that, right? So sine theta t cosine theta t is equal to sine theta I cosine theta I, right? And from the basic trigonometry, we know this formula: sine 2 alpha is equal to 2 sine alpha plus 2 sine alpha cosine alpha, right? Remember that formula? That's the trigonometry formula, trigonometry identity. Okay, and that means we can use this formula in this equation. So then if you multiply 2 on both sides, this thing would be sine 2 theta t, and this thing would be sine 2 theta I. Okay. Now if we eliminate sine and sine on both sides, then we'll get sine theta t equal to theta I, right? Is that right? So if you remove sine and sine, you get the angle to be equal. But that cannot be true. When the light is going from some less dense medium to denser medium, from air to glass, we know that light is bent towards the normal. So this angle, which is theta I, cannot be equal to theta t, right? That cannot be true. That means we need to do something else. Okay, that means we need to write. We can write what we can do is we can write. Let me write one more step here. So I can write this as sine 2 theta t is equal to sine 2, or I cannot go back. So pi minus 2 theta I, right? Because we know sine pi, or 180 degrees minus theta, is sine theta. That's true, right? That means I can write sine 2 theta I is equal to sine 180 degrees minus 2 theta, right? Because they are same thing. Now if I do that, then I can now equate these two things. I can equate this and that. Now this is not, that will not be the result of this. Let's discard that. So now we have sine 2 theta is equal to pi minus 2 theta I. Okay. And then I can take this to the left. I will have theta I plus theta t, and we have 2 also here, and I take this 2 on the bottom here. So that means theta I plus theta t is pi over 2. And this is the condition. Do you remember what is this for? What's the condition for? What was this condition true for? This is for when R parallel is 0, right? So you will not get any reflection or perpendicular parallel component of the electric field when this is true. Okay. When your incident angle plus transmitted angle add to pi over 2, then you will not get any light parallel to the plane. Okay. So now we can go back to our this equation, our previous equation. Or Snell's law, I mean. So here. So we have Ni sine theta I, okay, that's on the left, and then Nt sine theta t. This theta t is pi over 2. See, this is theta t is pi over 2 plus, sorry, minus theta I, right? So I can replace this theta t by that, pi over 2 minus theta I, right? And pi over 2, sine pi over 2 is sine 90 degrees, and sine 90 degrees is cosine, right? So Nt cosine theta I, okay? And then I can take the ratio of sine theta I over cosine theta I, and then I will get Nt over Ni. Okay. So this is sine theta I over sine theta cosine theta I is tan theta I. That is equal to Nt over Ni. And this is the angle of incidence. This is the angle of incidence for which R parallel is 0. So that means if you hit the boundary at this angle given by this expression, then you will not see any reflection that is parallel to the boundary. Okay, and this angle is called polarization angle. Polarization angle, and it's also called Brewster angle. Okay, also called Brewster, B-R-E-W-S-T-E-R, Brewster angle, which is denoted by theta b. It's also in our textbook it's denoted by theta p, but in some textbook it's also denoted by theta b. So that's the Brewster angle. So in the lab we'll see this phenomena. So when you hit any reflecting surface at this angle, you will not see any light, the parallel component of the light. So we'll look at this next time. Let's see, maybe we have a little bit of time. So now let's see how much we have. I think this one we can look next time, but I want to show you the graph here. This is the graph for the amplitude coefficient. So we have this R parallel, R perpendicular, T parallel, T perpendicular, like Fresnel's equations. Now we can plot all these things in the graph. So when we plot all these things in graph, we get these graphs. So what we see here is when this side is the angle of incidence. Okay, so this x-axis is angle of incidence, and this y-axis is these things. Okay, so for theta I is equal to 0 degrees, what do you see for R parallel and R perpendicular? Yeah, that's the value. That's the value, and the values are same in magnitude. They have the same magnitude, right? It's like this, which is like this first scale and the first division, and that's at second division, and this is also at second division. So they have same magnitude. Magnitude wise, it's same. Likewise, for the transmission also, it's same. The value is same. Okay, they have equal values for theta equal to 0 degrees. Also, theta equal to 90 degrees, they have same value. Theta equal to 90 degrees, they have same value. For the transmission parallel and transmission perpendicular, they have same value at theta equal to 0 degree and theta equal to 90 degrees. Same thing for the reflection coefficient. And we have a particular angle, which we call Brewster angle or polarization angle, which is that, at which you see this R parallel is 0, right? So at this point, R parallel is 0. So that's the Brewster angle. Okay. I think we will continue this next time. That's what we will use for our lab also. Yeah. Not exactly this one. So we will not be finding amplitude coefficient. We'll be finding the intensity actually. Yeah, because we cannot measure this in the lab, so we'll be finding intensity. It's a different kind of ratio, which is called transmittance and reflectance. Okay, that's all. If you have any question, I can answer your question.